Hello everyone, welcome back. In our previous video, we covered about AVL trees in a detail. We understood what are the unbalancing problems with the binary search tree, what is the balance tree, and what is the idea behind AVL tree cell balancing. And then we understood about the AVL tree rotations in a depth for insert operation. We will understand the AVL tree rotations for delete operations also. The rotations for delete and insert operations are same only, but there are some points which are different for delete and insert operations. We will cover those points in this video. So before actually starting on this video, I would recommend you to basically go through these two videos. This will act as a base knowledge and it will be easy for you to understand the terms which we will mention in this video. So let's start. Rotations. So the rotations for insert and delete operations are same. The logic is same, but the logic to find z, y, x, I mean, the logic to check what type of imbalance it is different between insert and delete operation. So we know that AVL tree finds three nodes, z, y, x, and work on rotating them to cell balance. So we know that z is the root of smallest unbalanced subtree. It is basically the smallest impacted area of the tree where balance is not 0, 1, or minus. Y is the taller child of z. So basically, when z is unbalanced, we need to know whether it is unbalanced because of the left subtree or the right subtree. So if it is unbalanced because of left subtree, it means the left side of z is heavy and y is the root of that left subtree. So basically, y is the taller child of z. So because of which subtree z becomes unbalanced, y represents the root of that subtree. Now x is different here. In case of insertion, the x is basically the node which is in an insertion path, because that is the path where height increases when we add a new node. In case of delete, we need to check which part of the basically particular subtree which is making heavy basically the subtree which is making z unbalanced. We need to check in that subtree one more level further. In that subtree, which side is taller, whether it is left side or right side, and that is represented using x, which is basically the taller child of y. So that way we can understand which part of the tree is more unbalanced and which type of rotation we need to apply. So let's understand one by one. So let's say we delete the node D here. So the balance at node Z becomes 2. So this is the smallest unbalanced subtree where Z is the root. So we found the Z. Now if you see balance is greater than 1, it means that the left side of the Z is heavy. So what is the taller child of the Z? What is the Y? It is the left child of Z. And what is the X? So for Y, which side of Y is heavy? It is left, because there are no nodes on the right side. So the left side is heavy. Basically, the height of the left subtree of y is heavy. That's why x is the left child of y. So it is the left imbalance. For a z, it is the left imbalance. So balance at z is greater than 1. And balance at y is greater than or equal to 0. It means it is left imbalance. So this is how we check the left imbalance in a delete operation. So it is little bit different from the insert operation. So this is the one of the difference between AVL insert and delete operation. So this is left case. Now in this case, if we delete the node D, the balance at Z becomes 2. So it means Z became unbalanced because of the left subtree of it. So that's why Y is the left child of Z. And for Y, the height on the right subtree is more, right? That's why it is left, right. So how do we check here? Balance at Z is greater than 1. It means it is left imbalance. But balance at Y is less than 0. It means it is more heavy on the right side. That's why it is left, right. The third case, let's say we delete the node D here. The balance at Z becomes -2, which is not allowed in the AVL tree. So -2 means that Z is unbalanced because of the right side of it. Heavy right side of it. So that's why Y is the right child of Z. And because the left side of y is heavy, because left subtree height is 1 and right subtree height is 0. That's why y is a left heavy. That's why the balance at y is greater than 0. It means it is right left case. So that is how we find the right left imbalance. And the last case, let's say we delete the node D here. The balance at node Z becomes -2, which means it is a right imbalance. So balance at Z is less than -1, but balance at Y is greater than or equal to, less than or equal to 0. It means it is right heavy. Basically, the right subtree of the Y have more height. So that's why. So this is how the 4 imbalance are detected in case of delete operations. So this logic is little bit different for insert and delete operation. But the rotation logic for each imbalance type is same for insert and delete operation. There is no difference. So for example, if we check the first imbalance case, which is left-left, this left-left imbalance is solved using right rotation in both insert and delete operation. And the steps are same. And we have covered this right rotation in much detail in our previous video. So please go ahead and check it to understand so that it will be easy to understand the further parts of this video. So the right rotation is used when node is too heavy on the left side. It means it is left-left imbalance. Right rotation means that basically Z comes onto the right side and Y becomes the new node. Right? It rotates the tree to the right side to fix that imbalance. What are the steps? So let's say these are the subtrees T1, T2, T3, T4 are the subtrees for X, Y, Z. Now the steps are the left child of Z, which is this one, becomes a new node because it is the right rotation, right? So Y will move here. So the left child of Z becomes new node and Z becomes the right child of Y. Why? Because Z is greater than Y. So where Z will go? Z will become the right child of Y to make sure that binary search tree property are maintained. But then what happens to the right child of Y? Because now because Z became the right child of Y, so the previous right child of Y, it will become the left child of Z. Because if Y becomes root, T3 is greater than Y, so it needs to be on the right side. But T3 was less than Z previously. That's why T3 will become the left child of Z. So it is the standard right rotation logic, which we had covered in our previous videos. To understand in a better way, let's say Y became new root, Z became the right child of Y. Now T3 and Y link is broken. So for Z, previously the left child of Z was Y. So this link is also broken and this link is also broken. So T3 is less than Z. So T3 can safely become the left child of Z. So this is how the right rotation works. To take the example with the delete operation, so let's say we delete the node 70 here. In that case, the imbalance basically it will cause this subtree to become unbalanced because the balance at node 50 will be 2. 2 minus 0, 2. 2 means the balance is greater than 1. It means it is left imbalance, left heavy. But so that's why Y is a left child of Z. But for Y, the balance is basically greater than or equal to 0. It is 0 actually, right? 1 minus 1, 0. That's why we'll take X as a left child of Y. So it is a left. So how can we solve the left? Using right rotation. Right rotation at Z. So we'll perform the 1 and 2. Left child of Z, which is 30. Left child of 50 is 30. It becomes the new root. And Z becomes the right child of Y, which is great. Now the link between 30 and 40 is broken. To maintain the binary search tree property, 40 will be on the right side of 30, like how it was here. But it was on the left side of 50. So that's why it will become the left child of 50 here, like this. So this is the standard right rotation logic, which is similarly deleted insert operation. Now let's understand the second type of imbalance, which is right imbalance, right imbalance. So right imbalance is solved using left rotation, basically moving the tree onto the left side. So What are the steps here? We do the left rotation at Z, which is our root of smallest unbalanced subtree. So when we do left rotation at Z, when we do the left here, then Y will become the new root here. And Z becomes the left child of Y. Why left child of Y? Because Z is less than Y, right? That's why Z will become the left child of Y to maintain the binary search tree property. And if Y had a left child of, if Y had any left child, because if Z becomes the new child, left child of Y, then this link between Y and T2 is broken. So where the T2 will go? Now T2 is less than Y, so that's why it will be on the left side. But T2 was greater than Z. That's why it becomes the right child of Z. So it is the standard left rotation logic. Like this. Y became new root, Z became the left child of Y, and the link between Y and T2 is broken. So if Y had any previous left child, then it becomes the right child of Z. So let's understand the logic. Basically, let's understand this rotation using example with a delete operation. So let's say previously the balance is 1 minus 2 minus 1. Now if we delete the 40, the balance becomes minus 2. 0 minus 2 minus 2. And so the taller child of 50 is 60. This is Y, right? Because right side of 50 is 80. For Y, the balance is basically 0. 1 minus 1, 0. So we know that in this case, basically, if the balance is less than or equal to 0, it means it is right-right imbalance. So for right-right imbalance, we do the left rotation as discussed in a previous slide. So we do the left rotation, 50 became the left child of Y, 60 became the new root. Now link between 50 and 55 and 60 is broken. So where 55 will go? 55 will go onto the left side of 60. And it was on the right side of 50 before. So that's why it will become the right side of Z. So this is the left rotation logic using delete operation. It is same as insert operation only. So let's understand the next rotation type, which is left-right rotation. We know that left-right rotation is used when the tree is a left-heavy, means left imbalance, but it is left imbalance, but it is caused because of the right side or right child of the left subtree. So basically, if you see here, the balance at Z is 3 minus 1, 2, which is greater than 1. But the balance at Y is 1 minus 2 minus 1. Means it is Y is a right heavy. So Z is unbalanced because of the left side, but Y is unbalanced because of, or not unbalanced, or because it is heavy because of the right side. So that's why it is left, right. And that we check using this logic. So in case of left-right rotation, we know that we need to have two rotations. First rotation is at Y to break this zigzag structure. And then next rotation is a right rotation at Z, because if you break the zigzag structure, it will become the left-left imbalance. And left-left imbalance can be solved using the right rotation. So why do we require two rotations or double rotation in this case? That we have explained in very much detail in our previous video. So please go and check it out. So without double rotation, if you don't do double rotation, then tree will be still unbalanced. That's why we need to have a double rotation. This is the high level, basically the reasoning behind it. For more details, you can go and check out the video, previous video. So what we do, left rotate at Y. So we do that and we break the zigzag. Good. And then we do the right rotate at Z. It means that left child of Z becomes the new root and Z becomes the right child of new root. And if the new root had any previous right child, it becomes the left child of previous root or Z. So this is how the left-right rotation works. Let's understand with the delete operation. So in this case, let's say we delete the node 80. So we know that standard BST delete operation. So when you delete the node with only one child, that child of that deleted node becomes a child of child of the parent of the deleted. Like this, let's say if 80 deleted, then 90 becomes the parent of, 90 becomes the child of 70. So the balance at 70 is 3 minus 1, 2. So 2, it is greater than 1, it means it is left imbalance. So y is the left child of 70, which is this. But at at y, the right subtree have more height, right? Because the left subtree height is 1 and the right subtree height is 2. So it is right side is more, it is right heavy. So that's why it is z, y, x. It is left, right. So what we do left rotation at y, which is 30 to break the zigzag structure. So tree will become like this. 50 becomes the new root, 30 becomes the left child of that 50. Now the link between 50 and 40 is broken. 40 is less than 50, so it will be on the left side according to the binary search tree property. It was on the right side of 30, that's why it becomes the right child of 30. So it is the standard left rotation logic which we saw in the previous slide. And then we do the right rotation at 70. Basically, the left child of 50, z becomes the new root, and the z becomes the right child of new root. And then if suppose if there was any node which was the right child of new root, it would have become the left child of the 70, but there is no right child here. So that's why no change. But it is the standard right rotation logic. So now we can see that 3 became balanced again. 2 minus 2, 0. So this is the left-right rotation example. Now let's understand the last rotation, which is right-left rotation. So right-left rotation means that at a node Z, which is the smallest impacted or unbalanced tree. So it is unbalanced because of the right side heavy, 1 minus 3 minus 2. So right side heavy. But it is unbalanced because of the left child of the right subtree. So it means that it is right imbalance. Balance at Z is less than minus 1. But balance at Y, which is the taller side of Z, is greater than 0. It means it have more height on the left side. So that's why it is right, left. So in this case also we perform the double rotation. First is right rotation at Y to break the zigzag structure like this. Right? So once we break the zigzag structure, then we do the left rotation at Z. So Z will become on the left side, X becomes the new root. And X had a T2 left child, so it becomes the right child of the previous root, which is Z. So standard left rotation logic. Right, left. And why it requires the double rotation? Similar to left-right rotation, it is required to break that zigzag structure and then perform the single standard left rotation or right rotation. It is explained in more detail in previous video, so please go ahead and check. But yeah, that is the high-level reason. We do right rotation at Y to break the zigzag structure and then do the left rotation at a impacted subtree root, which is Z. Now let's understand with the delete operation. Now we delete the 50 here, let's say. And we know that when we delete the node with the 2 children in a binary search tree, the in-order successor replaces that node. So what is the in-order successor of 50? It is 70. So 70 will replace the 50. So now it replaced the 50. Great. But when this happened, 80 became unbalanced. 0 minus 2 minus 2. So minus 2, which is less than minus 1, it means it is right heavy. But it means that the right child of 80 is a Y. But Y have more height on the left side. Right? 1 minus 0, 1. So it is right, left. So how can we solve? Basically, we can solve it using right rotation at Y, which is 90. So right rotation at Y is 90 becomes the right child of 85. And tree will look like this. It broke the zigzag structure. And then we do the left rotation at Z, which is 80. So left rotation means 80 becomes the left child of 85. Basically, the 85 becomes the new root. And 80 becomes the left child of 85. And the tree will look like this. So it is the standard left rotation logic. It is nothing different from what we discussed in a couple of slides before, the left rotation and right rotation. So this is how the tree will look like after rotation, and it is balanced now, 2 minus 2, 0. Now we saw that the rotation logic for insert and delete is same. Only the way we check the imbalance and decide Z, Y, and X is little bit different. So checking what type of imbalance it is only the difference between delete and insert operation. But one major difference between insert and delete operation in AVL tree rotation is that single delete operation can cause multiple rotations till root. Right? We'll understand how. So let's say this is the example. This is balanced. You see 3 minus 4, which is minus 1, which is allowed. So it is balanced. But now let's say we delete the node 60 here. So now if you see, the node 50 became unbalanced, right? 2 minus 0, 2. What type of imbalance it is? According to the imbalance logic for delete operation, it is greater than 1. It means it is left side AV. So taller child of 50 is this one, 40. So Y is this, left child of 50. And Y have a more height on the left side. So left subtree is high. So that's why it's the left child of Y. So this is left situation. So in case of left, we know that we can simply apply the right rotation at Z. Okay, we apply the right rotation at Z. So the left child of Z becomes the new root, and previous root becomes the right child of new root, and the tree becomes balanced again. So it is 1 minus 1, 0. So it is balanced. But now the tree became unbalanced on an upper layer. So basically, the unbalanced problem bubbled up to the ancestor from here to its ancestors. Right? So how? The height is 2 here. 2 minus 4 minus 2. So it became unbalanced here. What type of unbalance it is? So it is minus 2. It means the right side is heavy. So the taller child of 70 is 100. So Y is this 100. And for 100, the left subtree have more height because it is 3 and this is 2. So it is left heavy. So that's why ZYX is this ZYX. It is right left. So in case of right left, we know that we perform right left rotation. First, right rotation at Y. So the 90 become basically the new root, and 100 becomes the right child of 90. The link between 90 and 95 is broken. So according to the standard right rotation, we know that if the new root had any previous right child, it becomes the left child of the previous root. So it will become like this. Now it became left imbalance. So it basically we remove that zigzag. So we want to do right left rotation. So right rotation we did at Y. Now we need to do the left rotation at Z. So which is 70. So how we will do? So the taller child of Z, which is 90, becomes the new root. And Z becomes the left child of that new root. And if the new root had any previous left child, right? If it had any previous left child, it becomes the right child of the previous root. Right? This is how the standard left rotation works. So we did right rotation at basically previous 100, and then we did the left rotation at 70. So now if you see, the tree became balanced again. Right? 3 minus 3, 0. So we saw that this is the major difference between the insert and delete operation AVL rotations. In case of insert, the impacted area is only the small area where the node is added because height is increasing there, and we balance it and fix it there itself. But in case of delete, the height is decreasing, and when you balance it at the down level, it is possible that the unbalanced problem can bubble up to its ancestors or till the root, basically. So that is the major difference between the insert and delete operation AVL rotations, and that we need to handle for delete operation. This bubble up we need to handle in the delete operation. So in the next video, we will understand the implementation logic for insert and delete operations and rotations associated with it. And we will cover all the 4 rotations. So in this video, we covered basically how the imbalance logic is different for delete operation. And then we covered 4 rotations logic, which is similar to the insert operation and delete operation. And then we understood this major difference where the single delete operation can cause the multiple rotations till ancestors or till root. So hope you understood the video and explanation about the AVL tree rotations. If you like the video, please share and subscribe. Thank you so much.